Let's talk a bit more about the applications of the curl, the differential operator we recently learned about. You've seen that it's really helpful to understand the flow of the fluid, the vortices and so on. And it's also extremely useful to understand key processes in electric and magnetic fields. So here you see two examples of where the curl is really critical to formulate fundamental equations which govern electric and magnetic phenomena. So there is an equation which relates a curl of electric field to the magnetic field and the curl of magnetic field to the electric field. And J is the just current density, which can be constant. And mu naught and epsilon naught are fundamental magnetic and electric constants. So they're properties of the physical reality. Right. What I would like to talk now is some properties of that operator and also how it relates to other differential operators of vector calculus. Let's think about a curl of the gradient, because what you can do, you can apply these operators sometimes in combinations, in pairs. So let's first take a gradient of a scalar field and then take its curl. So by taking the gradient you get a vector field, let's call it V, and it's follows standard definition. So the question is, what will be the curl? Again, by definition, the curl will be just a determinant of that particular matrix. Let's look at the z component first. Let's just compute the z component of the curl of that vector field. So by definition, it is the derivative of the y component with respect to x minus the derivative of the x component with respect to y. Or if we remember that the y and the x are themselves relate to the f, then we can say that that is Vx and that is Vy. So we can write it as partial derivative with respect to x of df with respect to y minus partial derivative with respect to y of the vector field with respect to x. Or we can say that this is the second order partial derivative of f with respect to x and y minus second order special derivative with respect to y or x. But from the properties of the partial derivatives, we know that it doesn't matter which order you differentiate, it's the same. So they cancel out and result will be 0. So there is no z component of the curl. And likewise, you can show that the other two components, the y and x components, are 0. What it means is that if you take a curl of the gradient of any scalar field, you will always get 0. And that is the first property. So this is what you also can call a second order differential operation, because you apply derivatives twice, but the result of it is 0. And you can think of why is that 0? and I leave it for you as an exercise, but please consider discussing these in Piazza. So what is the dramatic meaning of that? And as I said, it's true for any scalar field for which you can apply the gradient. Now let's look at the example. Let's say somebody asked us to compute the electric field corresponding to a potential, which is a minus gradient, which you can also write in the Nabla notation. And I'm interested to know what is the curl. And according to that property, curl of the gradient is 0. That is why the curl of electric field for which exists an electric potential is always 0. So there are no vortices in such electric fields. Let's look at another type of iterative operation. Let's take a divergence of the curl. So first take a vector field and write down its curl, and then let's apply a divergence to that curl. So curl produces a vector field, and we can also apply divergence to a vector field. And we write by definition that it will be the derivative of the first component of the curl, of the second, and of the third with respect to y and z. Okay, we can simplify it one step further by expanding the brackets. Again, you have second order partial derivatives, and you can see that we have z here and z here, which are the same. The only difference is the order of differentiation, which is irrelevant. So we can cancel that out. Likewise, we have a pair of y which again cancel each other. And finally, we annihilate the derivatives of x, of the x component. And there's nothing left. So again, we see that this is 0. So taking divergence of the curl of any vector field is 0, which is another property. And speaking of applications, let's think now again of our moving fluid. Let's think that v is velocity field of this fluid. And if we want to know the vorticity, we take a curl, which will be a vector field again. And if we take the divergence of the curl, then we see that it's 0. That is why divergence of vorticity of any velocity field is 0. So that was examples and properties of the curl, which completes our study of the differential operators of the vector calculus.